Far out in space, something scary just happened.
You are about to hear a discussion of a first in the history of exploration.
Craft just wasn't sending back anything that we could unravel back on Earth. It was all nonsense.
NASA's Voyager 1 spacecraft is communicating again to ground control.
Is sending usable information to Earth again after months of spouting gibberish.
Object that we detected in space that you believe could possibly have been extraterrestrial.
For nearly half a century, Voyager 1 has sailed silently through the shadows between stars. But now, something has changed. What did Voyager find out there in the great beyond? Is it a glitch in the system, or a glimpse of something alien? This could possibly be the moment that rewrites our understanding of the universe. A story that's part science, part adventure, and just a little bit spooky. What secrets is Voyager 1 hiding? And are we ready for the answers? History of the Voyager missions. On September 5, 1977, an extraordinary journey began at Cape Canaveral, Florida. Voyager 1, perched atop a powerful Titan IIIe Centaur rocket, blasted off into the cosmos.
3, 2, 1. MDS, we have ignition, we have a liftoff.
Just 15 days later, on August 20th, its twin, Voyager 2, followed suit. These launches marked the beginning of one of humanity's most ambitious space exploration missions. The primary goal of the Voyager probes was to study the gas giants of our solar system, Jupiter and Saturn, along with their moons. However, these intrepid space travelers would go on to accomplish far more than anyone had initially imagined. As they ventured beyond their original targets, they broke record after record, becoming the longest operating spacecraft and traveling farther from Earth than any human-made object before them. Now, over 46 years later, both Voyager 1 and Voyager 2 continue their epic journey, having traveled more than 12 billion miles from Earth. But what makes these probes so special? How have they managed to survive and function for nearly half a century in the harsh environment of space? The Voyager probes were built to last, equipped with instruments that could withstand extreme temperatures and cosmic radiation. They carry computers with just 69.63 kilobytes of memory, about 3 million times less than a modern smartphone. Yet these ancient systems continue to process and transmit valuable data back to Earth. One of the most fascinating aspects of the Voyager missions is how they've continually surprised scientists with unexpected discoveries. For instance, when Voyager 1 approached Jupiter's moon Io, it detected strange signals. The subsequent images revealed something astounding. Io was home to active volcanoes, making it the most volcanically active body in our solar system. One of its volcanoes, Pele, was observed erupting to heights greater than Mount Everest, covering an area nearly as large as France. The Voyager's cameras captured over 33,000 images of Jupiter and its moons, revealing the gas giant's stunning complexity and the diverse landscapes of its satellites. These discoveries forced scientists to radically rethink their understanding of our solar system's outer reaches. But the surprises didn't stop there. Voyager 1 made another groundbreaking discovery when it detected Jupiter's faint ring system, adding another layer of intrigue to the already fascinating planet. Meanwhile, Voyager 2's flyby of Jupiter's moon Europa revealed a thick, icy shell over 60 miles deep, sparking speculation about the potential for life in its subsurface oceans. As the probes continued their journey, they used a clever technique called gravity assist to slingshot past the planets, gaining speed and conserving fuel. This cosmic dance allowed them to visit multiple planets and eventually break free from the sun's influence, venturing into interstellar space. Even as the Voyagers pushed further into the unknown, they continued to make history. On February 14, 1990, at the urging of astronomer Carl Sagan, Voyager 1 turned its camera back toward the inner solar system. From a distance of 3.8 billion miles, it captured the famous pale blue dot image, the most distant photograph ever taken of Earth, showing our planet as a tiny speck in the vast cosmic ocean. Despite their age and the immense distances they've traveled, the Voyager probes continue to send back valuable data. NASA has employed clever power management techniques turning off non-essential systems and heaters to extend the mission's lifespans. These efforts should keep the probes operational until at least 2030, allowing them to continue their role as humanity's most distant emissaries. To fully appreciate the Voyager mission's ongoing impact, we need to understand how they communicate across such vast distances. So how exactly do these far-flung probes manage to send their precious data back to Earth? And what role does the Deep Space Network play in this cosmic conversation? Data transmission in Voyager 1's discoveries. As Voyager 1 and 2 ventured deeper into space, they became our eyes and ears in the cosmos, sending back a treasure trove of data that has revolutionized our understanding of the solar system and beyond. The probes have remarkable communication systems. Each Voyager is equipped with a high-gain antenna, about 12 feet in diameter, which transmits data back to Earth using radio waves. These signals, traveling at the speed of light, still take over 21 hours to reach us from Voyager 1's current position. The data rate has slowed considerably over time, from an initial 115,000 bits per second at the start of the mission to just 160 bits per second today. That's slower than the first home internet modems of the 1990s. Despite these limitations, the Voyagers continue to make groundbreaking discoveries. One of the most significant came in 2012, when Voyager 1 became the first human-made object to enter interstellar space. How did scientists know it had crossed this cosmic threshold? The key was a dramatic change in the surrounding plasma environment. Voyager 1's plasma wave instrument detected an abrupt increase in plasma density, jumping from about 0.08 electrons per cubic centimeter to about 0.06 electrons per cubic centimeter. This sudden change indicated that the probe had left the bubble-like region created by our sun's solar wind, known as the heliosphere, and entered the denser plasma of interstellar space. But the discoveries didn't stop there. As Voyager 1 pushed further into this uncharted territory, it encountered something completely unexpected. In 2013, the probe detected a faint, mysterious hum, a continuous emission of plasma waves. This low-frequency sound, about 40 times fainter than the plasma waves previously detected at the edge of the heliosphere, has persisted ever since. What could be causing this cosmic background noise in the seemingly empty void of interstellar space? While scientists continue to ponder this question, Voyager 1 has been busy making other surprising observations. In 2020, the probe's data revealed that interstellar space is not as empty as once thought. It detected small bursts of cosmic rays, suggesting that the boundary between the heliosphere and interstellar space is a complex, turbulent area where particles from inside and outside our solar system mix and interact. Meanwhile, Voyager 2, which took a different path through the solar system, has been making its own unique discoveries. In 2018, it became the second spacecraft to enter interstellar space, providing scientists with a valuable comparison point to Voyager 1's data. Interestingly, Voyager 2's transition into interstellar space was slightly different from its twins. It detected a much sharper boundary, with the plasma density jumping by a factor of about 20 in just a few days. One of Voyager 2's most intriguing findings came from its study of the heliosphere's shape. For years, scientists had believed that the heliosphere was roughly symmetrical, like a comet with a round head and a tail. However, Voyager 2's data suggested something quite different. The probe found that the southern hemisphere of the heliosphere is much more compact than the northern hemisphere, indicating that the entire structure might be more asymmetrical than previously thought. But perhaps one of the craziest discoveries made by the Voyagers relates to the very nature of our galaxy. As they've traveled through interstellar space, both probes have detected higher than expected amounts of cosmic rays. This suggests that the magnetic bubble surrounding our solar system might be weaker than we thought, allowing more cosmic rays to penetrate our neighborhood of space. These cosmic rays aren't just interesting from a scientific perspective, they also pose challenges for the probes themselves. The high-energy particles can interfere with the spacecraft's electronics, causing occasional glitches. In fact, in 2020, Voyager 2 experienced a significant anomaly that temporarily halted its science operations. Thanks to the talent of NASA engineers who sent commands over 11.5 billion miles to reboot the probe, Voyager 2 was brought back online and continues its mission. Despite their age and the harsh conditions of space, Both Voyagers continue to operate thanks to their radioisotope thermoelectric generators, or RTGs. These ingenious power sources convert heat from the decay of plutonium-238 into electricity. When they were launched, the RTGs produced about 470 watts of power. Today, that output has decreased to about 249 watts for Voyager 1 and 252 watts for Voyager 2, still enough to keep essential systems running. The Voyager's journey through space has been nothing short of extraordinary, but their ability to navigate the vast distances between planets and make precise observations relies on more than just their onboard systems. How did NASA engineers manage to guide these probes on their complex trajectories? And what role did the planets themselves play in this cosmic story? Gravity assist maneuvers in the Deep Space Network. The success of the Voyager missions hinges on two crucial elements: the clever use of gravity assist maneuvers in the indispensable Deep Space Network. These components allowed the probes to journey farther than any human-made object and maintain communication across vast cosmic distances. Let's start with gravity assists, a technique that transformed space exploration. Imagine playing a cosmic game of billiards, where planets are the balls and spacecraft are the cue ball. That's essentially what gravity assists do. They use a planet's gravitational pull to slingshot a spacecraft, increasing its speed without using fuel. The mastermind behind this technique for the Voyager missions was Gary Flandreau, a young graduate student at Caltech's Jet Propulsion Laboratory in the 1960s. Flandreau discovered a rare alignment of the outer planets that would occur in the late 1970s, allowing a spacecraft to visit all four gas giants, Jupiter, Saturn, Uranus, and Neptune, in a single mission. This grand tour opportunity would not occur again for another 175 years. But how exactly does a gravity assist work? As a spacecraft approaches a planet, the planet's gravity pulls it closer, accelerating the probe. As the spacecraft swings around the planet and departs, it retains some of this speed boost. Interestingly, while the spacecraft gains energy, the planet loses an infinitesimally small amount, so small that it's immeasurable. The numbers behind these maneuvers are staggering. When Voyager 1 used Jupiter for a gravity assist, it gained about 35,700 miles per hour. To put this in perspective, the fastest aircraft ever built, the X-15, reached speeds of only about 4,520 miles per hour. The gravity assist from Jupiter more than doubled Voyager 1's speed relative to the Sun. Voyager 2's journey showcases the power of multiple gravity assists. It used Jupiter's gravity to increase its speed by 37,280 miles per hour, then Saturn's to add another 13,670 miles per hour. These boosts were crucial for reaching Uranus and Neptune, which Voyager 2 visited in 1986 and 1989 respectively. The precision required for these maneuvers is mind-boggling. A miscalculation of just a few meters in a spacecraft's position could result in a massive deviation over the vast distances involved. For instance, when Voyager 2 flew by Neptune in 1989, it passed just 4,950 kilometers above the planet's North Pole. This flyby had to be timed perfectly to use Neptune's gravity to deflect Voyager 2 southward, out of the plane of the ecliptic where the planets orbit. While gravity assists propelled the Voyagers through space, the Deep Space Network kept them connected to Earth. The DSN is a global network of giant radio antennas that communicate with interplanetary spacecraft. It consists of 3 facilities spaced approximately 120 degrees apart around the world: in Goldstone, California, near Madrid, Spain, and near Canberra, Australia. This positioning ensures that as Earth rotates, we maintain constant communication with our far-flung explorers. Each DSN complex houses several antennas, including massive 70-meter dishes. These antennas are so sensitive they can detect the incredibly faint radio signals from the Voyager probes, which have a power of less than 20 watts, about as much as a refrigerator light bulb. But just how faint are these signals? By the time Voyager 1's signal reaches Earth, its power is about 0.1 billionth of a watt. That's like trying to detect the light from a 10 to the power of a negative 12-watt bulb from 12 billion miles away. Yet remarkably, the DSN not only detects these signals, but can also extract meaningful data from them. The DSN's capabilities have grown alongside the Voyager mission. When the probes launched in 1977, the network could receive data at a maximum rate of 115,200 bits per second at Jupiter's distance. Today, with improvements in technology and technique, the DSN can handle much higher data rates from that same distance, up to 5.7 million bits per second. One of the unsung heroes of the DSN is Dr. Leslie J. Deutsch, who played a crucial role in developing the coding systems that allow clear communication over such vast distances. Deutsch and his team created a system called concatenated coding, which combines two types of error correction codes to ensure data integrity. This innovation has been critical in maintaining communication with the Voyagers as they ventured into interstellar space. But the DSN isn't just about receiving data, it also sends commands to the spacecraft. In 2020, when Voyager 2 experienced a glitch that shut down its science instruments, DSN engineers faced a daunting challenge. They had to send a signal strong enough to reach the probe over 11.5 billion miles away and reboot its systems. The signal, traveling at the speed of light, took more than 17 hours to reach Voyager 2. After an anxious wait, the team received confirmation that the commands had worked, and Voyager 2 was back online. This incident highlights a fascinating aspect of deep space communication: the enormous time delays involved. When Voyager 1 entered interstellar space in 2012, it took about 17 hours for its signals to reach Earth. Today, that delay has increased to over 21 hours. This means that any conversation with the Voyagers is an exercise in extreme patience. A round-trip communication can take nearly 2 days. Despite these challenges, the combination of gravity assists and the Deep Space Network has allowed the Voyagers to achieve feats once thought impossible. They've visited all 4 gas giants, discovered new moons, observed planetary rings we didn't know existed, and became the first human-made objects to enter interstellar space. The Voyager's journey through the solar system has been nothing short of extraordinary, but as they venture into interstellar space, they're entering truly uncharted territory. What lies beyond the bubble of our sun's influence, and what might the Voyagers encounter as they journey through this vast, unknown realm? The Oort cloud, heliosphere, and interstellar space exploration. Let's start with the Oort cloud, a theoretical region that marks the outer boundary of our solar system. Named after Dutch astronomer Jan Oort, who proposed its existence in 1950, the Oort cloud is thought to be a vast, spherical shell of icy bodies surrounding our solar system. The Oort cloud is incredibly far away. Its inner edge is believed to start at about 2,000 to 5,000 astronomical units, or AU, from the Sun, with 1 AU being the distance from Earth to the Sun. The outer edge might extend as far as 100,000 to 200,000 AU. That's nearly halfway to the nearest star, Proxima Centauri. To put this in perspective, at their current speeds, it would take the Voyager probes about 300 years to reach the inner edge of the Oort cloud, and a staggering 30,000 years to pass through it completely. This vast distance makes direct observation of the Oort cloud impossible with our current technology. But what exactly is in the Oort cloud? Scientists believe it contains trillions of small icy bodies, comets in waiting. These objects are thought to be leftovers from the formation of our solar system, flung outward by the gravitational effects of the giant planets. Occasionally, the gravitational pull of a passing star or other disturbance might send one of these icy bodies hurtling toward the inner solar system, becoming what we see as a long-period comet. As fascinating as the Oort cloud is, the Voyager probes are currently exploring a different region, the boundary between our solar system and interstellar space. This boundary is defined by something called the heliosphere. The heliosphere is a bubble-like region of space influenced by our sun. It's created by the solar wind, a stream of charged particles flowing outward from the sun at speeds of about 1 million miles per hour. This wind inflates the heliosphere, pushing against the interstellar medium, the gas and dust between star systems. But how big is the heliosphere? Its size actually changes based on the sun's activity. When the sun is more active, the heliosphere expands. When it's less active, the heliosphere contracts. On average, the boundary of the heliosphere, called the heliopause, is thought to be about 120 AU from the Sun. Voyager 1 made history when it crossed the heliopause on August 25, 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed suit on November 5, 2018. But how did scientists know the probes had crossed this invisible boundary? The key was a change in the surrounding plasma. Inside the heliosphere, the plasma comes from the Sun and is hot but sparse. Outside in interstellar space, the plasma comes from the explosions of giant stars millions of years ago. It's colder but much denser. When Voyager 1 crossed the heliopause, it detected about a 40-fold increase in plasma density, confirming its passage into interstellar space. This transition wasn't just a simple crossing of a clear boundary. The Voyagers revealed that the edge of the heliosphere is a complex, turbulent region. Voyager 1 observed two distinct zones in this boundary region: the depletion region, where the solar wind particles decrease, and the magnetic highway, where particles from inside and outside the heliosphere mix. One of the most surprising discoveries in this region came from Voyager 1 in 2013. The probe detected a mysterious hum, a continuous emission of plasma waves at frequencies much higher than the plasma's natural oscillations. This cosmic background noise has persisted ever since, raising intriguing questions about the nature of interstellar space. What's causing this constant hum in the seemingly empty void between stars? The probes have also made surprising discoveries about magnetic fields in interstellar space. Scientists expected to see a significant change in the direction of the magnetic field when the Voyagers crossed into interstellar space. However, the observed change was much smaller than predicted, suggesting that the magnetic fields inside and outside the heliosphere are strangely aligned. These discoveries are reshaping our understanding of the boundary between our solar system and interstellar space. Rather than a clear, distinct border, it appears to be a complex, dynamic region where the influences of our Sun and the interstellar medium interact and overlap. Looking ahead, the Voyagers still have more to explore. They're expected to continue operating until around 2025, when their radioisotope thermoelectric generators will no longer supply enough power to run their scientific instruments. Even after they fall silent, they'll continue their journey through the Milky Way galaxy. Voyager 1 is traveling at about 38,000 miles per hour and is headed toward the constellation Ophiuchus. In about 40,000 years, it will pass within 1.6 light-years of the star Gliese 445. Voyager 2, slightly slower at 35,000 miles per hour, is headed toward the constellation Pavo. In about 296,000 years, it will pass within 4.3 light-years of the star Sirius, the brightest star in our night sky. Even as the Voyagers push deeper into interstellar space, new missions are being planned to further explore this frontier. NASA's Interstellar Mapping and Acceleration Probe, scheduled to launch in 2025, will study the boundary of the heliosphere from Earth orbit, complementing the Voyager's direct measurements. The Voyager missions have expanded our cosmic horizons, transforming our understanding of our solar system and its place in the galaxy. As these explorers continue their journey into the unknown, they carry with them a message from Earth, the famous golden records, containing sounds and images representing the diversity of life and culture on our planet. In billions of years, when our sun has long since faded, the Voyagers may be the only evidence that humanity ever existed. Finally, we turn the questions to you. What might future generations learn from the Voyagers' silent passages near distant stars, long after we're gone? And how might our understanding of the cosmos change as we continue to push the boundaries of our exploration? Start the conversation in the comments section below. Smash that like button, subscribe now, and hit the notification bell to stay on top of all our uploads. The universe is full of surprises. Make sure you're here for the next one.